Well, here we are at Palomar Observatory, arguably the most famous observatory in the world. And behind me is the dome that houses the 200-inch telescope. And what better place than to be at Palomar Observatory to talk about telescopes and how they're used in astronomy. Now, a little bit of history of the observatory. Palomar Observatory was originally funded in the early 1920s. It was constructed in the middle of the 1930s. And by the late 1940s, the telescope was open for business and ready to be used for astronomy. The telescope was the brainchild of a man by the name of George Ellery Hale, who was very famous for building very big telescopes. And the original idea was to build the world's largest telescope. Previously, the largest telescope in the world was the 100-inch telescope at Mount Wilson Observatory, a little bit further to the north from us here in Los Angeles. And Hale wanted to build a telescope that was much bigger than that to be able to observe the universe in a way that had never been seen before. The original money that was raised to build this telescope came from the John D. Rockefeller Foundation, and for a sum of about $6.5 million, Hale was able to put together a team of engineers that would build the world's largest telescope. Now, because the telescope was so big, the engineering breakthroughs that were necessary to build a telescope of this scale were some unique features unto themselves. So in many ways, Palomar Observatory is an engineering marvel. And once we go inside, we'll get to see the telescope and see how the telescope works. But let's talk about the dome that is housing this large telescope. Every observatory has observatory domes that the telescopes reside inside, and the purpose of the dome is to protect the telescope from the elements. You want to have a nice place to keep all of the elements away from the telescope during the daytime, and you also want a way to protect the telescope at night, allowing only part of the sky to be viewed at any given time. Inside of the dome, the temperature is much lower. It matches the outside air temperature so that tonight, when they open the dome and use it for their astronomy, that it will be ready to go at a moment's notice as soon as it gets dark. Now, what we're going to do is go inside and get a chance to see the function of the telescope, how they operate, how this particular telescope was put together, and of course talk about some of the details as to why we use telescopes in astronomy. So as I mentioned, every telescope's primary purpose is to gather light. And essentially a telescope is just a giant bucket. The more light you gather, the brighter objects will look. In the early days of telescopes, the problem was that the largest opening to telescopes only allowed so much light to go through. You could not gather very much light because you had no ability to make an opening to a telescope big enough to accommodate a lens much bigger than a certain size. So it was actually Isaac Newton who discovered that you can achieve the same results of a typical telescope with lenses, but instead of using lenses, using a mirror. And so every telescope that is a research-sized telescope around the world today uses a mirror called a primary mirror to be the part of the telescope that does the light gathering. So essentially you have a curved mirror that is not a flat mirror, but again has an indentation to it or as a concave curvature to it. And the purpose of the mirror is to sit at the bottom of the bucket of the telescope. The light passes through the bucket, it bounces off of the curved mirror, and because of the curvature of the mirror, the light will be forced to come to a point, which is what we call a focal point. And in the old telescopes with lenses, that point where the light comes to a focus is where you put your eye. But in modern telescopes, what we do is we put equipment right where that focal point would be instead of your eye. Now, the 200-inch telescope has one additional feature to it, and that is to be able to put equipment at the bottom end of the telescope itself, to be able to hang the heavy equipment that's used to analyze the light. The equipment is held underneath the mirror. And so the mirror has a hole drilled into the middle of it that allows the light to bounce off of the mirror, come up to a focus, but instead of coming to a focal point, it bounces off of a second mirror, and the light is sent right back down through the opening in the telescope. And this is called the Cassegrain hole, or the Cassegrain opening to the telescope. So the 200-inch Hale telescope is called a Cassegrain style telescope because of this one design feature. Back in the 1920s, the largest telescope in the world was again a 100-inch telescope of this very similar design. But the engineering challenge of the day was how can you build a telescope mirror that is twice the size without all of the trouble of having a very, very heavy piece of glass. And so what was done was a couple of engineering designs to help mitigate this problem. You can see in this scaled down model of the actual mirror that exists in the tube of the 200-inch telescope. What they did was the form that was used to make the mirror has many of these sort of pilings that you can see that were at the bottom of it. 114 of them that were blocks that were put into the original mold, so that when the glass was poured into the mold and filled up the mold, eventually these sort of geometric shaped blocks would be taken out, and you would have cavities all over the backside of the mirror, which thus reduces the overall weight of the mirror. When the mirror was originally poured in the mid-1930s, the piece of glass that ultimately ended up being the single mirror weighed about 20 tons. And the ability to have these small indentations in the back in this honeycomb design actually reduced the weight of the telescope mirror by about 45%, meaning it would have been a much heavier piece of glass if these were not incorporated. Now, once the mirror was poured, it was very much like this disc. A hole in the middle, a round mirror, but is totally flat on its surface. After the mirror was poured in New York, the mirror was then sent as a disc across the United States to the city of Pasadena, where Caltech had a very, very sophisticated laboratory that was used to grind the mirror and get it down to the appropriate shape so that when the light passes through the telescope and hits the mirror, it will eventually come to the correct focal point. So even though this is a much smaller version of the idea, and we have a scaled down version of the actual mirror that is in the telescope behind us here, the idea is very much the standard of today. And even the largest telescopes in the world, although the mirrors are becoming much, much bigger than the Hale 200-inch telescope, the design of this curved mirror with the hole at the center, this Cassegrain design, is still the design that is preferred to this day. The 200-inch telescope is no longer the largest telescope in the world. In fact, there are a little more than 20 telescopes that are currently larger than this telescope. But the basic design of this telescope is still fairly the same throughout the world. Now, during the daytime, the telescope is stowed in this position. This is the home position where the workers during the day have easy access to the equipment that's at the bottom of the telescope. The mirror is down in this portion of the telescope right here. The opening of the telescope is up here. The light from your object that you're looking at comes in, reflects off of the primary mirror, and then comes to either a focus at the top, or you can redirect the light back down through the Cassegrain hole in the bottom. To be able to move the telescope, to be able to aim it at your object, or to be able to track the object that you're looking at throughout the night, the telescope needs to move in two different ways. The first direction that the telescope will move is in a north-south direction, in this case pointing all the way to the north celestial pole of the sky, and then has the ability to point from north all the way down to a certain position to the south. So this gets you the north-south movement of the telescope. And then the telescope has the ability to move from east to west, and that's what the horseshoe allows the telescope to do. So the mount is a very critical part of the telescope. It allows you to move the telescope around the sky and to line up on the object that you want to study. Throughout the night, though, once you have the object of interest in the view of the telescope will slowly track over the course of the night. So when the object has been found, very, very slowly, the telescope is going to move in essentially an east to west direction, very slowly. And this is what we call tracking. The idea is that you want the telescope to steadily move and track the object that you're studying, because the natural rotation of the Earth would normally make the object move out of the field of view of the telescope. So once the telescope is aimed at the object of your interest, then very slowly over the course of the night, the telescope will track, and forever long you want your observation to be, and then you can move the telescope on to the next target, and then of course you can track for that target as well. The telescope itself is 50 feet long. It has an opening of about 22 feet across. The horseshoe design has an edge-to-edge diameter of about 46 feet. The telescope, the mirror, and the mount all together weighs 530 tons, almost a little more than 1 million pounds. And so the engineers back in the 1920s and 30s had to come up with a very, very creative way to be able to balance this telescope and allow it to move quite easily. Using ball bearings would have been impossible because the sheer weight of the telescope would have crushed the ball bearings. So instead, in this gap right in here, there are oil pressure pads that when you turn on a motor, it injects oil into these pressure pads, and it literally raises the telescope just a tiny fraction of an inch. And then it is so well balanced that when the clutches are turned off, just the fact that somebody could lean on the telescope will actually cause the telescope to move. That's how well balanced this telescope is. So for the 1920s and 30s, the engineering itself to make this telescope a reality was just absolutely marvelous, and it was one of the most creative ways to solve the problems of the day, and still to this day stands as quite an engineering marvel. Well, it brings me great pleasure to be joined with the astronomer who's going to be using the 200-inch telescope tonight. Joining me is Steve Howell from NASA Ames Research. So Steve, can you tell me a little bit about the research that you're doing tonight?
Sure, Mark. Pleasure to have you guys here. So tonight we're observing some objects that are in the field of view that the Kepler spacecraft has observed for the past 4 years. And while Kepler is most famous for finding planets orbiting other stars, tonight we're actually observing stars that are called white dwarfs. These are stellar remnants, stars that have died and are very old and very compact. So they're a star about the size of the Earth, but they have about as much mass as the Sun jammed into that small size. And white dwarfs are very important to the Kepler mission for 2 reasons. There's the science reason. There's a lot of interest in knowing what happens to stars when they die. But white dwarfs are also an incredibly photometrically stable object. That means that the light from the white dwarfs hardly varies at all. So they're a very nice calibration target for the Kepler spacecraft.
So Kepler has been a spacecraft that's been in the news quite a bit lately. Can you tell us a little bit more about the Kepler spacecraft?
Well, the spacecraft is a space telescope, so to speak. It was launched in 2009. It doesn't orbit the Earth. It actually orbits the Sun. Currently, it's about half an astronomical unit away from the Earth and getting farther away every day. So at some point in about 4 or 5 years, no matter what, we would have to stop communicating with it because it would literally be on the other side of the Sun from us. It's a 1 meter Schmidt type telescope. It has a very large focal plane array of CCDs. It's the largest focal plane that's ever been flown into space for astronomy purposes. And it has stared at one part of the sky for 4 years, and that's a part of the sky that lies between the constellations Lyra and Cygnus.
Excellent. So obviously you're here on the 200-inch telescope to do this follow-up research. Is there a particular reason why you chose the 200-inch telescope to do this research?
Sure. I mean, the 200-inch is very old and honorable telescope, right? A lot of cool research has been done here. But the 200-inch is still a very large telescope. It has a nice instrument on it called the double beam spectrograph, and it allows you to observe the object in essentially the entire optical spectral region at one time. If you would go to some other telescope, you might have to spend twice as long to get the same data. You might have to, on one night, observe in the blue part, for example, and the next night observe in the red part, where we get both of those at once here. So the large size of the telescope and the unique instrumentation on it are the reasons we're here.
Very nice. So can you tell us a little bit about how your evening would progress? What does an astronomer do? A lot of people will ask me just that. What does an astronomer do when they're at the telescope? Can you just tell our audience a little bit of what your night will be like tonight?
Sure, absolutely. So this afternoon I've been putting together my observing list. I have about 100 objects that I hope to observe over the next 3 nights. So I've been putting together that list. That list consists of some name of the object, usually something that's like a telephone number, some big long coordinate number, the coordinates in the sky, and something about the brightness of that object. That list goes to a place in the telescope control system where we can then, throughout the night, just literally click on an object and the telescope will slew to that object, will move and point to that object.
10 minutes?
What do you think for this one, Steve?
This will probably be 2 times 15,
Okay.
I would guess.
How bright is it?
17 and a half or something like that.
Okay.
I think it'll be pretty easy to find.
Ready to move?
Yep.
Yep.
Okay, we are there if you want to check the field. I would assume it's the star nearest the fiducial.
Yep. All right. Okay. That's our boy.
It is. And we're guiding. We're there.
Yeah.
So I have that list put together. I started doing some calibrations. The calibrations for this instrument are pretty straightforward. Over here we can see one of the calibration spectra. This is a iron argon lamp, FEAR. Some people have called it a fear lamp. There's nothing to fear. And this is a lamp that's filled with nothing but emission lines. It's a lamp that literally sits in the spectrograph. You turn it on, you take a spectrum of it, and those emission lines allow you to calibrate your wavelength scale so that you know where you're looking in the spectrum to a very precise value.
Excellent. And on this screen over here, it looks like there's a photograph of a spectrum.
That's right. This over here is that spectrum, but just an image directly off the CCD.
Okay.
So in order to sort of be able to see that better and make more precise measurements, you can visually look at it and get some idea of what you see and make sure the exposure looks right. But then you need to make a plot. So you literally just drag your line down all those lines and you get a plot that looks like that.
So this screen here is a graphical version of what visually this screen is.
That's right. Exactly.
Excellent.
Yeah.
Well, the weather looks spectacular outside.
It does indeed. It's
is
very
your
exciting.
equipment running well?
The equipment's running well. The staff here set up the spectrograph that you run from this monitor here. It's a great job they always do, and we're ready to go.
Well, I thank you for your time, and I wish you luck on your run. So here we are out on the catwalk of the 200-inch telescope, and observatories are often places with more than one telescope, and Palomar Observatory is certainly the case. Back in the 1930s, it was originally planned to have 4 telescopes here on the mountain. The 200-inch telescope, there's a 60-inch telescope, there's a 48-inch telescope, and the very first telescope that was actually put on the mountain was an 18-inch telescope, although it's out of commission today. Observatories are typically places that are on the tops of very tall mountains, and the reason for this is so that we can be as high up in the atmosphere as possible. The idea is that you want to be very, very high in elevation so that the amount of air that's above the top of the mountain is very thin. The problem that we have is starlight that comes from very, very far away places has to work its way through the atmosphere before it reaches the telescope. And if the atmosphere is turbulent, then the images of the stars become unstable. That creates the twinkling that you might have seen when you look at stars. So if you're down at sea level, there's more atmosphere to look through, there's more twinkling that the stars will have, and it's very difficult to learn things about the stars. Being on the top of a very tall mountain reduces the amount of air you have to look through, and so therefore the views of the stars, the views of galaxies are very steady. In addition to being where the air is very thin, when you're on the top of a very tall mountain, you tend to be in places that are far away from cities. The light from cities is at night something that makes the sky glow, and if the sky glows brighter than the stars, then you can't see the stars, and we call that light pollution. On the top of a remote mountain, you tend to be far from cities, far from city lights, and light pollution isn't as much of a problem. Additionally, being at the top of a very tall mountain means that the weather is something that you can perhaps be more away from the bad weather that typically occurs at lower elevations. We're about 35 miles here from the coast here at Palomar Observatory, and so the air that comes off of the coast is very stable. The marine layer that often covers San Diego doesn't make it up here, and so astronomers can continue to work with clear skies when the city might still be socked in with bad weather. All of these features together are what make it very important to choose the right location, and typically on the tops of very tall mountains will satisfy all of these issues.